Well, good morning, afternoon, or evening. Welcome to week 5 of the semester. This week we get into global temperature trends. It's a pretty straightforward lesson, so I hope you take the time to really make sure you cover it well. It is not difficult material, yet very important that you understand how it ties back to previous lessons and how this information is used in subsequent lessons. So please bear that in mind. Without further ado, let's put this into presentation mode and get going. So present climate change. So what's happening now? Okay. From 1880 to 2019 per the IPCC AR6, which came out in 2021, the mean annual temperature increase basically has been an increase of 1.09 Celsius or 1.96 Fahrenheit for that period. And again, if you recall back to previous lessons, the majority of this heat has gone into the oceans, not the atmosphere. So it has gone into the ocean. So you can think of possibly more energetic storms when they do form in the ocean as a result of that added heat. Over about 1.2 through early 2021. So it continues to increase. This number will change from year to year, but in the end, we're looking at trends. Remember, that's the idea. You need to focus on trend, not necessarily year to year variability. So let's look at some of the details of this information. Today, basically, CO2 stands at about 420. Depending on when you're watching this, it could have been slightly lower, slightly higher, but let's just go with this number. It is an increase of 2.5 parts per million per year. So every year is higher than the year before. That's a very reliable thing to say. It's the highest increase in 15 million years, and that's you're going back to not only ice records, but geologic records. 21 of the 22 warmest years have happened in the 21st century, and the only 20th century exception would be 1998, and that happens to be a very strong El Nino year towards the end of the 20th century. We had back-to-back hottest years on records, 2014, 15, and 16, with 2016 still holding the record barely as the number 1 or hottest year in the books. 2020 number 2, 19, 17, 15, and 21. Basically, the increase per decade has been about 0.2 Celsius or 0.36 Fahrenheit per decade since the 1970s. Again, you need to focus on trends. Next year, 2023, might be a cold year, comparatively speaking. That doesn't mean that climate change has ended or global warming has ended. It just simply means there's a down year compared to previous years. And then it may go up yet again. So it's a trend that you need to focus on. Here is the idea of carbon dioxide concentrations at Mauna Loa. So official records began in the year 1958 at Mauna Loa in Hawaii. First of all, a little bit of a review. Why Mauna Loa? It sits in the middle of the Pacific Ocean, and really, really high up in the atmosphere, so it's not affected by industry and cities and all the trappings of modern day society. So that's one thing to remember why Mauna Loa. The other is the ups and downs. It almost looks like the blade of a saw. Up, down, up, down, up, down. And the ups happen to be when it is winter in the Northern Hemisphere, because the Northern Hemisphere has more trees. So therefore, in winter, when the trees are down, so basically starting in October into November and December, all the leaves will fall, and then the planet has a lesser ability to soak or suck up some CO2. So concentrations go up. When we get into the spring of the Northern Hemisphere and all the trees begin to bloom again, suddenly the planet has the ability to suck up more CO2, so it goes down. But bottom line, the trend should be that this this is lower than this, that is lower than that, and so on. There might be a few exceptions in the data, but by and large, almost without exception, every year's peak is higher than the previous year's peak. That's just one of these like very difficult to refute facts. Notice in 1958, we were about 318 parts per million. We are basically about 420 parts per million now. So we've gone up by more than 100 parts per million in basically less than 70 years, which is a remarkable thing to observe. And then this is as far back as you can go with ice core data. So this is basically looking at ice core data in not only Greenland, but Antarctica. And notice that this is where we are now at 420. Notice how high, it only went as high as about 300 parts per million before. So this is the idea of humans having a significant impact on the concentrations of carbon dioxide on a planetary scale. All right, here's a way of looking at data. So this is yet another way of looking at data. Again, you need to focus on the trend. Again, I need to highlight and really emphasize 0 does not mean 0 degrees, but it means normal global temperature. Meaning, this is what the temperature should be. So for example, when you have a fever, that means your temperature is higher than 98.6. So for a human body, 0 would be 98.6. You get that? I just need to make sure that you understand where we're going with this, right? So a positive number, so a number in the red means a warm anomaly. And the term anomaly means different from what it should be. And a negative number means a cool anomaly. Notice since about the year 1977, every single year has been in the red. So every single year has been a warm anomaly. And notice the past 7 years, so 2021, 2019, 18, 17, 16, and 15. All right? So this is a very simple yet remarkably important graphic to understand. Here's another way of looking at the data. Going back to 1851, year by year, and then within each wheel, it tells you how each month looked. Notice how the darker colors, how it gets darker in terms of orange and red by the time you get to the year 2020. Notice that since about the year 1965, there has only been 1 month that's been considered cooler than average in that entire period. And that would be the month of February in 1974, or this one here, October in 1976. That's it. That's the last time you see any bit of blue in these little wheels. Notice 2016, the hottest year on record. So collecting temperature data done at thousands of stations globally. Air temperatures over land and weather stations are collected. Over the oceans, ships, buoys. They're combined on a regular grid, and basically you sample every square kilometer of the Earth's surface. The urban effect or the urban heat island in large cities is excluded. And if you've never heard of this term, it simply means that if you're in cities like New York and Los Angeles and London, big cities tend to always be hotter than the environment around them, because big cities are made up of metal and cement, and they have lots of air conditioning units and asphalt and, buildings that trap heat inside of them. So urban heat islands are excluded from global calculations. And so here's another way of looking at data. Remember, this is to give you a sense of what the 7 hottest years have been, in addition to going back to the year 1850. Again, you need to focus on a trend. This graphic has been basically repeated in this presentation already at least 3 or 4 times. It is simply a way of making you look at the data in a different way. That's all. Again, 0 does not mean 0 degrees Celsius. It just simply means this is what it should be. It should be, normally the temperature should be around here. And if you think about it, that would be around 59 degrees Fahrenheit. So this would be 0.2 above 59, 0.4 above 59. Get it? That's where we are. And then this right here, if you go back, we've already covered this in a previous lesson, but the idea of an annual temperature, so each individual little black dot versus Lowe's smoothing, which is basically a 5-year running average. So the individual dots give you annual ups and downs, whereas the red line gives you, oh, there's that word again, trend. You need to remember that. That's really what climate change and the study of climate and climate change is about. It's understanding trends. So you need to sort of keep that word in mind. Again, the strongest El Nino of the 20th century was in 1998. And the eruption of Mount Pinatubo in 1991. Notice what a significant cooling that led to. So volcanic eruptions, aerosols, lead to cooling of the global system. But it's usually temporary, okay? This was covered in a previous lesson, as was this. So just because you cooled down significantly from 1990 to 1991 and 92, doesn't mean that climate change ended. It simply means a volcanic eruption got in the way. And frankly, that's not what you want, to cool down the planet anyway. So as stated already, we're going to focus on trends, long and short. So there are 3 that I want to address. So let's begin with that one, then that one, then that one. Notice one is a positive, one is roughly stable or neutral, and the current one we're in is significantly high. So let's look at the first one. 1910s to the 1940s, it was a warming trend. Solar intensity increase, greenhouse gases increase. Remember, the United States was becoming a rapidly industrialized nation at that point. And so that is the first trend. The second trend, that would be the 1940s to the 1970s, stagnant. While solar activity remained constant and greenhouse gas concentrations increased, the warming was canceled by awful pollution, because pollution tends to have a cooling effect. That's not necessarily a good thing. That's not what you want to happen in order for cooling to take place, because industrialization and pollution have their own negative effects associated with them. And now the third one, the current one we're in, the late 70s to now, solar intensity constant, aerosols have been cleaned up because we've become really, really good at fixing pollution. And the greenhouse gas concentrations have accelerated, leading to that. So that's where we are basically right now. So those are the 3 trends that you need to focus on. Here's another way of looking at data. So this is the increase in temperature by decade. So notice the 1950s, 40s, and 60s were pretty much close to that 0 line, normal. but then the 70s, the 80s, the 90s, the early 2000s, and 2011 to 2020. So that's where we are. Obviously, you can see the trend. You can see that trend in here, just like you can see it in here. This is year by year. This is decade by decade. But it's just a different way of looking at the same data. And here's another way, a little bit more numerical way of looking at the data. So the rank, how much of warming has taken place, warming in Celsius, warming in Fahrenheit. And you might say, but wait, 1.21, 1.36? I thought it was 1.09. Remember, this is for the individual year. That number at the beginning of the lesson, 1.09, is for the period 1850 to 2019. So you have to understand the temporal scale used. This is for the individual year. Make sense? Hopefully it does. So it is clear that that period, 2010-2020, was warmer still than the period 2000 to 2010. 9 of the 10 hottest years on record have been observed during the past decade. And more than likely, by the time we get to the year 2030, and this is just a presupposition on my end, every hot year is going to be in the 2020s, more than likely, or at least in this century, meaning from 2000 all the way to the end of 2030. So how reliable are the data? And by the way, data are plural. So this is the correct grammar here. Global warming, climate change is not, and should not be anyways, a political position. It is, sadly. So climate data, climate change data is all about information and observations that are collected on a global scale. Again, they're collected by meteorological stations that follow strict collection protocols and rules, and the data are freely available to anyone, anywhere. There is no denial of that data to anyone, and it is free to collect. So here's the idea of a false claim. Scientists, one of the things that makes scientific and academic inquiry so tricky at times is that it is subject to the peer review process. That is where you submit your findings to a body of other scientists who then really, really closely and anonymously puts the data through significant rigor in order to figure out if it's incorrect, if there's something that needs to be addressed, and so on. So that's the idea of the reliability of scientific data. Many times when errors are made, papers are retracted and things are corrected. So it is a very, very tightly regulated process. So these are the folks who monitor global temperatures. So NASA Goddard in Maryland, the Met Office at the Hadley Center in the United Kingdom, NOAA in Washington, D.C., and of course, the Japanese Meteorological Agency. These are at least the big 4 institutes that do this. Now, when you look at the data and you do 4 independent analyses, they show remarkable agreement. So here are many, in fact, there's 5 different analyses of temperature. And hopefully you can see that even though they are not perfectly matched, what does match is the ups and the downs of the data. And the difference really stems from computer coding, basically, just to make something really complicated as simple as I can. Bottom line is the agreement is remarkable. They all show the same trend. Remember that? Notice how you have in the 1940s and 1970s a very stagnant look, an increase now, and a negative or a warming trend rather, prior did that. Can you see that? Can you see how this image looks like many of the other images we have shown, or that have been shown during this presentation? That's all I really need you to get out of this. The basic agreement between all these different institutions and the fact that they look remarkably like the previous images shown. Again, that's the key takeaway. So how unusual are the current trends? Over the last 20,000 years, there's really no simultaneous warming of the northern and southern hemispheres that has been observed. The Arctic, which basically the north and south ends of the world, the North Pole and the South Pole, they're experiencing a warming that is significantly much more pronounced than any other region of the world. Here's again another way of looking at the data. This is an actual animation from a previous, but what I want you to get out of here is, notice temperatures are higher over land than over the oceans. Oceans tend to have a sort of moderating effect on temperature. And the northern hemisphere is warmer than the southern. And that's because there's more land in the northern hemisphere than there is in the southern hemisphere. The southern hemisphere is much more covered in water than the northern hemisphere is. And the majority of the industry and people live up here rather than down here. That's just one of those things. Okay? They've been verified by these different locations. The NCDC, which is the National Climatic Data Center in Boulder, Colorado, NASA, the UK Met Office, and again, the Japanese Meteorological Agency. And of course, printed in report form and compiled by the IPCC. So if you're looking at the idea of looking up, went there a little too far, again, the increase per decade in the lower troposphere, so basically where we live, this has been the increase from about 0.18 to 0.32 per decade since 1981. And surface weather stations over land report a 0.2. So this is when it's average land and ocean. This is land only. So the lower troposphere is warming, the heat is trapped, and it insulates the layer above, which means the lower stratosphere, which is the layer above where we are, where the weather happens, that is actually cooling. And because we're making the blanket of greenhouse gases in the lower troposphere much more efficient at trapping heat, we're preventing some of that heat from making it to the next layer. Therefore, it is cooling. And it's cooled by about 1.5 degrees since 1950. And there's been a significant loss of ozone, although we are fixing this. So that absorbs UV light, which also leads to cooling, because you're losing some of the energetic interaction between the UV light and the ozone. So here's the idea. Here's the troposphere warming, red colors, right, in this side of the bar. There you go. Deserts. Notice significant cooling in Antarctica. That's the only exception. So here we have the Sahara Desert, the Mexican and American deserts, the Sonoran and the Mojave. Here you have the Tibetan Plateau in Western China. And of course, the opposite of that would be, so this is the troposphere, which is located above this layer. So this is the stratosphere. This is from the ground to the top of what we call the atmosphere where weather happens. Again, the troposphere, the lowest part of the atmosphere. And then the next layer is just above that, and it is cooling. All right? And the most pronounced cooling is over Antarctica because that is where the most ozone has been lost. So, did warming end after 1988? In 1988, it was a very warm El Nino or strong El Nino year, which tends to be a warmer year globally. Remember, 2016, the hottest year on record, was also an El Nino year. 2008 was dramatically cooler, okay, but it's still on that red bar trend of warmer years. And then you have these, 2014, 15, 16, 17, 18, 19, 20, and 21. Again, you could theoretically look at 1 year and go, it went down. Look at that, it cooled. We're not warming, we're cooling. But again, what is that 5-letter word that I want you to focus on? Trend. What's the trend? What is the long-term trend? Is still warming. Again, here we go. You could say, but look, we cooled down. We were way up here, now we're here. Well, and then you warm up again, and then you go down, and then you go up again. And yet this point is still higher than that point, which is higher than this point, and so on. Get it? The blue line is the trend. Ocean temperatures, remember 91% of the heat goes into the oceans. The oceans are functioning as a storehouse, a storage house, or a sink. That's a better, more appropriate term, is where it basically is kept. And again, think about the idea of storing heat. So this may seem like that graph we saw earlier, but it's really not, even though it shows the same pattern. This is ocean heat compared to average. This is where the ocean heat should be. Notice how in the 1960s and 70s it was cooler. Then you have this up, down, up, down, up, down pattern. And then from about the year, 1995, so that would be 1994-ish. It's been in the red ever since. So, warmer than average ocean heat content since 1995, really 94. Practically runaway heating since then. So what does that mean? That means potentially stronger storms because there's more heat. Now, hurricanes, for example, require more than just hot water to form. So hot water isn't the only requirement, but it is one of the big requirements. Think of them as the fuel. And here's a way of looking at the data. So this is ocean heat storage. And we're looking at ocean heat storage in 3 different ways. Deep ocean storage, so that would be anything below 6,500 feet in depth. That would be this gray. Ocean heat storage between 2,300 and 6,500. So think of it as the middle. And surface ocean heat, from the surface, where you go to the beach, down to about 2,300 feet. And that is these lines. Notice how much higher how much higher the surface heat storage is compared to the middle ocean and the deep ocean. And the important thing here is, the key takeaway is, this is what hurricanes rely on and storms, because they're drawing it from the top of the ocean. So the majority of the heat is going into the upper ocean. It's remarkable if, you probably never get to do this. I will never get to do this. But even in like the tropics, if you go down pretty deep into the ocean is really, really cold. Even near the tropics, because there's no sunlight to really warm it up. So you can have remarkably cold water even in tropical regions if you go deep enough. Okay? So that's the idea of the lesson. It's pretty straightforward what we're talking about this week. Again, I think I mentioned the word trend like, I don't know, a whole bunch of times. So focus on that. That's the idea. Look at what the patterns look like. Again, do not confuse, again, 0 with 0 degrees or something to that effect. Think of it as the normal temperature that it should be. I always make the connection to body temperature, right? 98.6, that's what your temperature should be when you go to the doctor. Well, 98.6, a 0 difference from 98.6 means you're at 98.6. That's where you should be. Anything on the positive side, you have a fever. It's hotter. Anything below that, you're hypothermic, cold. So that's sort of what I want you to focus on. Straightforward lesson. Hope you do well. If you have any questions, please ask. Otherwise, I hope you have a fantastic week, and we will talk to you soon. Bye.